All right, so we will just briefly review today what was done in the video that I posted. So we are working through linear algebra review. And basically we're dealing with how to manipulate vectors and matrices. And most importantly, we started introducing matrices. So matrix is a general array that has m rows and n columns. It can actually keep going in dimensions, and vectors and computers do store multi-dimensional arrays that are much more difficult to show on the screen. But there is nothing preventing from computer to have an element in 5 dimensions: a, 2, 3, 4, 7, 23. Okay? So basically, I can keep going in dimensions, and computers don't care. It's humans that have harder time processing multidimensional data, okay? And specifically visualizing. But matrices are most, just because I can store the data, or sure, that doesn't mean that I can still manipulate it efficiently. So algorithms are improving, but matrices, two-dimensional matrices, are still the most common way to store the data. Now, standard operations of adding, multiplying by scalar, and just transposing or flipping the matrix rows and columns are there. Those are straightforward. We have a number of special matrices, so you just kind of need to refer to them by name, such as diagonal matrix that has non-zero elements only on a diagonal. So those are elements that have the index of a row and a column is the same. So A11, C11, B11, B22, B77, those type of elements are non-zero. Everybody else is zero. Identity matrix has ones and diagonals, and it's actually an important one because it has a property that A inverse A is equal to identity, as well as A inverse is equal to identity. So it's sort of an equivalent of number 1 for matrices. So when I have number 2, 2 times 1/2 is 1. 1/2 is inverse of 2. Okay? So 2 times 1/2 and 1/2 times 2 is 1. Okay? Therefore, those two numbers are inverse of each other. Well, there is an equivalent for that in matrix world. And this doesn't necessarily make sense to you, like why is it important right now, but we will actually be solving systems of equations. Ax is equal to b, and I'm looking for x being a vector. And in that sense, if I had an inverse, I could just multiply everything with that inverse, and voila, I have a solution. My x is A inverse b. So this is in the matrix multiplication. So there's a lot of applications for inverse. And we will actually get to, down the line in our lesson, lecture 6 or so, we will actually go ahead and work on the algorithm on how to compute an inverse. Symmetric matrix is equal to transpose. I can have more than one diagonal, so sort of like above and below the diagonal. I can actually keep going and have a tridiagonal, pentadiagonal matrices. And they're important in some applications. So there is a whole class of problems in numerical modeling that actually ends up having matrices of these types at the core of its problem. So you have to constantly solve a problem having this matrix. So that's how things have names. The moment you have something that shows up constantly, it's going to get a name. So in that sense, tridiagonal matrices are important. And we're going to get to the positive definite a little more again down the line. So quick review of multiplications of matrices and vectors, because that's going to lead us to matrix multiplication. So essentially, if I have m rows and columns, matrix, I can multiply that matrix with the vector that has the same number of rows as I have columns. Okay? So that's what we say that dimensions have to match. So if I have m by n, this has to be n by 1 if it's a vector, or it could be actually a matrix, n by r or something like that. Okay? So that allows me to actually then take, in this row view, so to speak, of the multiplication, I'm going to take, for instance, the first row, okay, and effectively do a scalar product between this row and this column. Okay? So scalar product simply sums up all of the a11 times x1 plus a12 times x2 and so forth, and adds those up. So this is my result, okay? And this is b1. Now if you see, if I actually now, and then I continue the same. Now if I actually see, if I take a look at these sums here, I can see x1, 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 yes? And here I can see like x2 repeated and xn repeated. So this appears, if I look at this as a vector, b1, b2 through bm, this vector, this should be n, I apologize. No, it's correct. This should be m. So if I look at this as a vector, this vector is x1 times this column as a vector, right? Plus x2 scalar times this column, yes? Plus xn times the last column of A. So this can also be seen as that my resulting vector is simply a linear combination of columns of this matrix with these coefficients. So there's just one way to look at it, okay? And that's what's actually done here. So basically I take first column times this coefficient plus second column times x2 plus all the way nth column times xn. So x1, xn, x2 all the way to xn are my coefficients, and this is a linear combination of columns, where columns are viewed as vectors. So this there's a term for this. Whenever I create a vector out of the linear combination of the others, that's called dependence. So I'm linearly dependent of the others. And typically when I'm defining space, for instance, two-dimensional or three-dimensional space, two-dimensional space means that there exists at most two linearly independent vectors that cannot be derived from each other. And any third vector I introduce into the mix can be shown as a linear combination of the first two. And that's precisely what we're using when I'm thinking that my dimensions in two-dimensional space of something are 2, 1, right? 0.21. It's 2 times my first vector, which is just the vector in direction x, plus 1 times vector in direction y. Right? The identity or the vector, unit vector. And that those unit vector in each of those directions are called basis vectors. So it's a base on which I'm basically representing all other vectors. And I can switch things up. Okay? So I can switch my basis. And there's a whole matrix, a whole lot of matrix multiplication in that, switching between one basis to another. But basically, what coordinate system I pick is dependent on my application. So in different coordinate systems, my coordinates 2, 1 might switch to something else if my bases are not those two unit vectors, but some other two vectors. And we constantly use that. In engineering, we constantly use that by switching from classical Euclidean Cartesian coordinate system, where things are equivalent to each other, to cylindrical or spherical. So, and those are also coordinate systems. It's just that in a cylindrical world, I have a cylinder right here. Okay? In cylindrical world, and it's obvious why cylinders are important, right? There's so much equipment that is cylindrical. Basically, I will have a center, I will have a radius, okay? And I will have still a z and I will have an angle. Okay. So I will have a starting point, and then I have angle in this direction. I have radius, so R, phi, and Z. And I can actually switch between the coordinate bases. Basically, I'm using matrices and multiplying one coordinate to get to the other. Have you done that in math, in any of the math classes? Yeah, we might need you to take note. Let's come up with homework. Switching coordinate systems. That's nice matrix multiplication problem. And it's very important. You're going to get that in some math class or the other. Maybe you you have to know how to switch coordinates. Obviously, if I'm flying a plane, I've got to know something that's very important. If I'm going to change my distance, okay? So we should, not that Earth is a perfect sphere, but also, okay? To get my point, it's important to switch coordinate systems. All right, and this is where these linear combinations of vectors are important. Now, matrix vector multiplication, again, it can be, it's resulting in a vector, okay? Vector matrix multiplication, okay, might not be easy, might not be the same, and that's something to, that is important to note. And we will actually look at both as matrix-matrix multiplication, so it's going to become clear. So if I actually have two matrices, and one of them is M by, in this case, R, and the other one R by N, then I can multiply them because I have matching dimensions. I have R columns here and R rows. So every time I look at two matrices, first thing that I have to do is, can I make this multiplication? And I can only if so-called inner dimensions match. Why? Because I'm going to proceed the same. So what we're actually going to do, let's actually get a little smaller example, just easier to look at. So let's say that I have matrix times a matrix here. I'm going to essentially, the first column here in my result, okay, will be this matrix times this vector. I know matrix vector multiplication by now. Then I'm going to just keep going. I'm going to multiply this times this and place it right there. And then multiply this times this and place it right there. So I can do it that way. I can also simply realize, every location in this new resulting matrix, let's say that I have Cij element, okay? That Cij element will be a dot product of my ith row in first matrix A and jth column in the second matrix B. So that's another way to look at it. Okay? So essentially, then my C22 over here will be simply A21 times B12 plus A22 times B22 plus A23 times B32. And that's my C2. But I have to, of course, repeat that to get. Now there's one important thing, is that in order matters a lot. So in regular numbers, when I'm just multiplying numbers, 2 times 3 is the same as 3 times 2. The operation is commutative. That's just the name for it. That's not the case in matrices. For one, my dimensions might not match, so I might not be even able to perform the operation, let alone that AB is equal to B. So that's something that is important. All right, so let's now get going, and I'm going to do a small example. I'm going to do it offline over here, and then we're going to just start working on the homework. So I'm going to stop recording for now.